Swayam Prabha. Digital India. Educated India.
In the previous session, we saw the case of the PLL where the PLL did not lock and it generated asymmetric beat node at its error voltage. Let me just write this as the loop filter here, followed by VCO and like this V in, V out. We had initial frequency error which was large, the PLL did not lock and it generated lot of voltage. Okay. Now, you think about it, for delta omega of 0 greater than k PD times k VCO, right, the error voltage generated generated a waveform which looked like this. This is our error voltage with respect to time. It had some DC voltage which we call that as pull in voltage. Now, the first question which we should ask is that why the PLL did not lock? Well, the PLL did not lock because the control voltage was not as required. Okay? You did not have the control voltage as required to lock the frequency. Just to repeat this, you can think about it that in order that I lock the VCO to the desired frequency or desired frequency error in the beginning, I should have omega in equal to omega out, and omega in initially is omega out is omega free times k VCO times Vc. So, the control voltage should be omega minus omega free by k VCO, or I have been using FR, right. This is delta omega 0 by k VCO. I should have this control voltage in a steady state. Okay. In the case which we are discussing, the delta omega 0 is pretty large and the control voltage which is generated by the PLL loop is not large enough. Okay. But one interesting thing which we found, that the error voltage which was generated in such a case, that particular error voltage has a voltage which has some DC positive value in this case. So, at this node you can say you are seeing some DC some voltage waveform like this. Okay. It has non-zero DC voltage. So, if I want to increase the control voltage, okay, this control voltage you need an steady state, which means that you need a DC control voltage which is large enough for the PLL to lock. If that is the case, then one can think about it that here, oh, I am having already some DC value which is non-zero. Let me amplify this particular, because this DC value is coming where? Well, this DC value is coming at VR. So, if I can, Vp is like Vp DC value is going to the loop filter. If I can amplify the DC value through the loop filter, I may be able to lock it, right. We were not able to do so because the loop filter which we have been using by 1 plus SRC, whose DC gain is equal to 1, we are not able to do it. Okay. So, if we were not able to do it, we want to give a large DC gain to amplify the voltage as we need. If we want to do that, then we can very well replace our loop filter with an integrator. Okay. We want a large DC gain. A large DC gain, an integrator is a block which gives you infinite DC gain. Integrator gives infinite DC gain. This is something which we recall. Okay. We have the pull in voltage, some non-zero DC value, we amplify with infinite gain. You can say we can surely get as large voltage as we want. So, we change our PLL from the previous one to the one where we integrated it, the error voltage. Whatever is coming, you just integrate it, you pass it to the VCO. Right. This is now your error voltage, this is control. So, assumption is that when we are going to do this, we will have this pull in voltage Vp here, and that Vp will actually get amplified or that integrated to give you a large control voltage. Okay. That is what should happen. But actually what happens is, when you have a large frequency error in this case and you start at time instant t equal to 0 with frequency error delta omega as omega in minus omega free, which is delta omega 0, this frequency error, all the initial values which you have as V error was 0, Vc is 0 to begin with. What happens is that V error voltage to begin with is nothing but half times sine of omega, let me just write delta omega 0 times t. I am neglecting the other part which is sine of omega in plus omega out. This I have been neglecting, assuming this is going to be filtered by the loop filter or the integrator. So, this part is neglected for now, okay, only this part remains. So, what you are doing when you start your PLL, you are feeding this sine wave to your integrator. Okay. You feed this sine wave to your integrator. Okay. Initially, the integrator output was 0. So, V control had no information about the phase error. All the information which V control can have about the phase error will come through the integrator. Okay. So, this will come through the integrator. The integrator input itself is a sine wave. Okay. So, what you will get if you integrate V error above, V error here, you are integrating a sine wave. Right. If you integrate a sine wave with DC value of 0, the average this integration over integral number of period of the frequency error is going to be 0. Okay. So, this is the problem, that when you use only integrator in this particular loop, to begin with you do not have actually pull in voltage, because the VCO does not have any information about the error. So, the frequency V control value was initially 0. So, it is like running in an open loop while not controlling the VCO frequency, and the average of sine wave is going to be 0. So, the average of, when you integrate using this 1 over tau I, if you want, I can write this 2 tau I and this value goes to 0. So, V control does not develop any DC voltage. So, PLL still does not lock. Okay. So, what do we need to do? We need to provide the pull in voltage for the integrator, and at the same time we need to integrate the pull in voltage to get the frequency locked. So, what we need to do is the following, that you give this as V in, this you get as V error. V error goes to two paths. One, the previous path which has like a DC gain of 1, you can think that way. So, now I will just use as proportional constant of value tau p by tau I, and another one with an integrator 1 over tau I times integral dt. These two things I am going to add somehow, do not worry about it how, and then this goes to VCO. Okay. Now, just try to understand it little intuitively, that you start this PLL with frequency error delta omega 0, you get V error, right, and V error is initially, we have seen initially when you are looking at, this is by the way V control, this I will call as Vi and this is V proportional, because there is a path from V error from tau p tau I going to VCO and coming back. Because of this particular path, we will be able to generate asymmetric beat note at the at V error value. Okay. And then because you are having asymmetric beat note, you have a pull in voltage Vp, which is a non-zero DC value, and this Vp gets integrated. You are integrating non-zero value. So, this Vp will keep getting integrated to increase the integral path output. This is integral path output voltage. Okay. So, I can say that the Vp from here, this Vp value from here gets integrated, and this increases our Vi. And when you increase Vi voltage, so in this particular case what will you write? You will write V control is tau p by tau I times V error plus 1 over tau I into integral of V error dot dt. Okay. This is what your control voltage will be. So, if I want to write the output frequency, omega out is nothing but k VCO times Vc. So, Vc has two parts, tau p by tau I times V error, another part is 1 over, sorry, k VCO will be here again, k VCO times V error part, where is V error, in V error you are seeing two values, one is the DC pull in voltage, another you can say if you remove the DC part from your asymmetric beat note, right, that is something that whose that average will be 0. So, you have your output frequency like this. Okay. This particular part will keep on increasing the frequency in the desired direction, such that the overall frequency error reduces. Okay. And it is only when the frequency error reduces, the phase error will also keep on changing, and at one point of time what you will see is that the phase error will be equal to 0. In a steady state, what you are going to see that the phase error will be equal to 0, voltage error will be 0 here, which means P proportional will be 0 in a steady state, and Vi will have whatever control voltage is desired to lock the frequency. Okay. Let me show you the simulation part for this particular analysis. Okay. So, in this particular plot, the same example, I have been using the same example, that our k VCO happens to be 2 pi times 100 mega radians per second per volt. Okay. And I am plotting here for the given frequency error. So, we will figure it out what frequency error we have. You see that the control voltage here settles to Vi, control voltage settles to 0.75, okay. And if it is 0.75, then the initial frequency error which I am having is 2 pi times 75 mega radians per second. So, this was my initial frequency error, which is actually greater than the 50 megahertz 2 pi into 50 megaradians per second, which we have seen earlier, where the PLL did not lock. So, one by one. So, when I had only proportional path, which is only the path using tau p by tau I, only that path, you see that the control voltage just keeps on creating these asymmetric beat nodes. There was no change. The PLL did not lock, control voltage just keep on changing. In case we had only integral path, then you see for the case only integral path, control voltage always keeps on, is a sinus, you are integrating sine wave, you will get cosine, right, and it keeps on integrating, and it never settles. Never settles means it never reaches a finite value, it keeps on changing. If control voltage keeps on changing, then the frequency of the oscillator will also keep on changing. Okay. So, that is what happens, but in case you see that in case we have both the proportional and the integral path, then the pull in voltage of this asymmetric beat node is actually utilized to integrate and finally achieve a fixed value for the on the integral path as shown here. And along the proportional path, what you are seeing is the phase error actually changes and finally it settles to 0. And whatever the integral path value you have, that gives you, that compensates for the initial frequency error.